Welcome back. In today's video we're going to be doing problem 40. I've already kind of started it, but yeah. It says a flywheel slows from 600 to 400 revolutions per minute while rotating through 40 revolutions. What is the angular acceleration of the flywheel? How much time elapses during the 40 revolutions? So it says revs per minute, so we write RPM as units. Rotating through 40 revolutions. So it's using revolutions this time. And so that means we have to multiply 40 by 2 pi, because one revolution is 2 pi radians. So, as always, we have our knowns, so let's write our unknowns. I don't know if knowns is a noun, but I keep using it as a noun, so our unknowns, and our unknowns are, what is the angular acceleration? So our alpha Greek letter here is our unknown, as well as our time during 40 revolutions. That's an unknown as well. So those are our two unknowns. We know our delta. Right, okay, this is where we wanted to do it. So we have 40 revolutions, but we can treat this, okay, let me just, okay. We have 40 revolutions, right? 40 revs, right? Over 1, because there's nothing, it's not per anything. Alright, so in order to cancel out revolutions, we want our revolution amount in the denominator, so it cancels. So we'll write our rev unit there, and we want radians instead, so we'll write that above. So how many radians are in one revolution? Well, it turns out there's 2 pi radians in one revolution, and that is exactly equal to the circumference of the circle. 2 pi r radians. Radians is just a unit for radius, if you didn't know that. So 2 pi r radians for one revolution. Alright, and so yeah, we're going to cancel everything, and so essentially all we're doing is multiplying by 2 pi. So that's what I was doing earlier. So if we just put that in our calculator, I guess we can kind of take a shortcut here and just say this is 80 pi, which is probably even more accurate. Well, it will be more accurate. So that's the correct way to go about it. Just move this out of the way. But yeah, just try to think about things in units as much as possible, because then it just makes everything fall into place, essentially. Alright, so it's asking for what is the angular acceleration of the flywheel. So let's go back to our kinematic formulas, or angular formulas, and we want acceleration. We don't have time, so we do have our delta theta. Let's see, what is our delta theta? It's this. And we also have our omega initial and omega final, but we have to convert that. So let's see. We don't have our acceleration. Okay, so we have to use this formula right here. Doesn't seem like there's any other formula that doesn't use time. So this is the one we're going to use. But firstly, let's go ahead and convert this to omega initial, omega final. So same deal as before, except we're introducing time now as the denominator, because there's per, so it's below the denominator. So let's go ahead and write this out. So 600 rev, I don't know if that's a real unit, I'm just imagining it, using my imagination. And then 1 min per minute. Yeah, so then it's good that we do convert this, actually, because we're going to have to write this. Alright, anyway. So the same thing as before, we're just gonna cancel out revolutions, cancel out minutes for seconds. So as before, we saw that one revolution is 2 pi radians, rad. Remember, this is a unit. And then we have 1 revolution. So these cancel. The radians is left behind, 2 pi radians times 600. And now we have to add another unit conversion factor. Another conversion factor, which is going to be from seconds to minutes. So since minutes is in the denominator, in order to cancel it, we have to add minutes in the numerator. So we know that 1 minute has 60 seconds, is equal to 60 seconds. So now these cancel. So now we're left with radians and seconds. Oops, seconds. So let's go ahead and write out the final answer, which is 1200 pi radians per second. So that is our initial, our omega initial, right? Yeah. And then our omega final will go through the same process. So 400 rev per 1 minute. Again, 2 pi radians. Make sure you write rad. I'm just going to write rad from now on so I know it's unit. I think I already did that, but rad versus r, so it's just straightforward. Alright, so then 2 pi radian is going to be 1 revolution. And we also have to cancel minutes with 1 minute equals 60 seconds. Boom, boom. Boom, boom. We have radians and seconds. Hopefully you're seeing how this is becoming pretty straightforward. So yeah, this is going to equal omega final equals 400 times 2, which is 800, times pi. No need to calculate this because it's irrational anyway, so this is actually a more accurate depiction of what we're trying to measure. And then we have to divide by 60 seconds though. Oh, I didn't do that here. Oh, yikes. Okay, we actually do need a calculator. Actually, no we don't, sorry. It's just gonna be 20. Right, 20 times 60 is 1200. So, sorry, this is actually 20 pi radians per second. My bad. So yeah, same thing here. We're going to divide 400 by 60. Maybe you can do that in your head. I'm not that good at it, so, but it's around 6.6 repeating. Does this make sense? Yeah. Ooh, sorry. I'm not mathing today. So yeah, I have to multiply by 2 first. 400 times 2 divided by 60. So yeah, this makes more sense. It's going to be 13.3 repeating. So yeah, those are the answers for our omegas, our angular velocities. So yeah, we can go ahead and do a little bit of cleanup here. So our omega initial is equal to 20 pi radians per second. And our omega final is equal to 13.3 repeating pi radians per second. Yeah. So those are the variables we know now. Oops, sorry. Let's give some space here. It's always good to manage your work because you want to look back at it eventually. Okay. All right. So yeah, everything looks good. So now what we're going to do, is find our acceleration. Yeah, sorry. So let's go ahead in our formula sheet. Whenever we want to find a variable, we just go straight to our formula sheet. Pretty straightforward, right? So yeah, we want our angular acceleration. So we have all the variables, so we can be kind of careless. Sorry, we don't have time, so we can't be careless. We have to use this one right here. So let's go ahead and start part A. So our equation is going to be the last one on the formula sheet. It's going to be omega final squared equals omega initial squared plus 2 alpha delta theta. So this is our equation. And yeah, all we have to do is plug in everything we have and solve for alpha. I'm going to do what I did last time though and isolate alpha first. I'll isolate the variable so it's just straightforward. You might do this on a test, but yeah, I think it would be a good idea to do it on the test. Just be careful, make sure you're isolating correctly. It's good to practice that now, you know, just brush up on basic algebra. So yeah, divide by 2, divide by delta theta. Kind of like doing it diagonal, but I don't know if that's standard. Anyway, so yeah, this is going to be equal to alpha, our angular acceleration. And so yeah, now we want to plug in everything we know. And just plug it into your calculator. Okay, 13.3 repeating pi radians per second squared minus your omega final squared initial. Your omega initial, which is 20 pi. And then divide by 2 delta theta. And delta theta should be an equal sign. Delta theta is 2 times 80 pi radians. So we get a negative acceleration. That's good because it says it's slowing down. It's always going to be the case when the final is greater than the initial. Or sorry, less. And we do see that. Alright, so I get an answer of negative 4.36. And then the answer, looking at the solution here, they have negative 4.4, which is just rounding to sig figs. So let's go ahead and write that. You can also check your work by checking their work, and we see that we did follow the correct steps, so that's good. And this is going to be radians per second squared. Alright, so this is our angular acceleration done for part A. So that's part A done. And let's go ahead and start part B. I wrote part A twice, whoops. So let's go ahead and start part B. So part B says how much time elapses during the 40 revolutions. So again, this is pretty straightforward. We just find the formula, find the equation. We can be there's a word that I want to use, but I don't know. Frugal, maybe. We can just pick whichever one we want. So I'm gonna go ahead and use the easiest one just to keep it simple. Try and always keep things simple when it comes to solving problems like this. It'll help you out. Alright. Okay, so it was omega final equals omega initial plus alpha times time. So I'm going to isolate again. We're finding time this time. Minus, whoops, yeah, minus both sides. And divide by acceleration. Okay, now you plug it in your calculator. Our omega final was 13.33 repeating. And our omega initial was 20. Sorry, and there's pi involved. So pi is concatenated on both those terms. And we get, I kind of wish it was in terms of pi, that'd be nice. Let's see. I don't think that's going to happen though. Then we want to divide by our angular acceleration, which we just found. Negative 4.4 or negative 4.36 might work. But our time we get is positive, which is a good sign. We get 4.75 seconds for our answer. And then rounding to 2 sig figs, we get 4.8 seconds. And that is part B done. So yeah, that's everything. Hopefully you found problem 40 solution helpful. If you have any questions, again, eventually I gotta stop saying that because I've said it too long. But yeah, if you have any questions, make sure to leave them down below in the comment section and like and subscribe. Thanks for watching.